Good morning, y'all. Some more take-home physics coming at you from one of the rooms in my house here. It's a bit of a mess, but we're framed, so it'll work. This is my special guest speaker, Rod. Say hi to Rod. Hi, Rod. And Rod is here to help us learn the difference between a center of mass and a center of gravity. So, what you don't know, this rod now, is a meter tall. Cool? And I have him here vertically on purpose. And what you also don't know is rod is uniform, just made out of steel, iron. So it's a very uniform density rod. What that means is if I were to count the number of molecules in this section of rod way down at the bottom that I'm highlighting with that blue tape. If you can't see it, it's no big deal. But what I mean is that bottom 1 centimeter of rod. If I were to count the number of molecules that's inside rod right there, I'd get a number, whatever it is, I don't know. But that would be rod's mass of that little segment of rod. You can call it a differential mass if you want. That number of molecules gives you a mass, which you can then multiply by lowercase g in order to get the weight of just that segment of rod. So m times g. That's easy. And I could do that along the whole entire section of rod, even way up at the tippity top of rod, 1 meter away from the bottom. This section of rod, I could do the exact same thing. I could count the number of molecules in that same sized section. I'll get the same number of molecules as I did down there because it's a uniform rod. That amount of mass I could then multiply by g, and I would get the weight of that segment of rod. And under the circumstances we're in here, this segment of rod would weigh exactly the same as that segment of rod because rod's only a meter tall. The mass is the same everywhere, and the gravitational field that it's feeling doesn't change. Okay? You will also know rod's center mass, since it's a nice uniform distribution of mass inside a rod. His center mass is the center of rod. That would be the 50 centimeter mark. That would be where I could balance rod, okay? So in this circumstance, rod's center mass and center gravity are exactly the same thing. And that's going to be the case for, by far, the most items on the planet Earth are going to have the same center gravity as the center mass, which is what I showed you with these meter sticks before, right? This meter stick is balanced at the 50 centimeter mark. The planet Earth only cares about that 50 centimeter mark. If I try to balance it at the 70, it'll rotate in the direction of that center mass. If I try to balance it on the 30, it'll rotate on the direction of that center mass. So the planet Earth does only tug on the center of the object. We'll call it its center mass. You can also call it its center gravity because they are synonymous when we are under these types of conditions. Now, what I want you to think about, though, is, ooh, nice. What if I take this rod and I stretch them out? And so now, instead of having a 1 meter rod, let's have a 10,000 kilometer tall rod, okay? And I do the exact same thing I just showed you with this blue tape down here. At the bottom of the 10,000 kilometer rod, I do the same thing I did before. I'm going to count the number of molecules in that section of rod. It'll be a number, same number as it used to be. To get the weight of that rod, section of rod, I would take that number of molecules worth of mass, multiply it by g, I'd get a number. Whatever it is, it is. But you know, g here is 9.8, right? But if I go way up to the top of a 10,000 kilometer rod and I count the number of molecules up there, that number of molecules will be the same as this number of molecules down here. That doesn't change. But what does change now is that little g is smaller. So this m times a little g means this segment of rod now weighs less than this segment of rod because it's farther away from the planet Earth. If it's a 10,000 kilometer stick, whatever, g has decreased as we go up rod, okay? Which means the planet Earth is literally tugging with more force on this section of rod than it is on that section of rod, which means the bottom section of rod is heavier. It's an M times a big G compared to the same M times a smaller g. So the bottom section of rod is heavier, which means the planet Earth is pulling downwards on the bottom section with more force than the planet Earth is pulling downwards on the top section, which has then the effect of pulling the center of gravity of rod closer to the Earth. So the center mass of rod stays the same. It's at that 50, it's at the midpoint. That's the center mass. That doesn't change because it's a uniform distribution of mass. But what does change now is the bottom half of rod is heavier, so the center of gravity is now lower than the center mass. So the center mass is an internal and intrinsic property. Sometimes physics comes from within. The center mass just depends on the distribution of mass and the shape of the object. The center of gravity depends on an external force, quite literally the force of the planet Earth, the gravitational field that this rod happens to find itself in, and if that gravitational field changes across the length of rod. So that's the difference. The center mass is internal. If it's a uniform distribution, it stays at the center no matter where I put it. But rod's center of gravity will change if it's a very, very, very large object and I place it in a gravitational field of something else, then that something else will pull with more force on one end than another end, which means it lowers the center of gravity towards, in this case, the planet Earth. And that's very accurate. That is true for very large objects. Sometimes buildings have different centers of mass than gravity. The moon, for example, has a different center mass than gravity because the planet Earth pulls with more force on the side of the moon that's closest to it than it does to the side of the moon that's farthest from it. And what that has the effect of doing is the moon tries to rotate, the Earth pulls it back down, if you will, but pulls its center of gravity closer towards it. So when you guys take a more advanced kind of physics or astrophysics class, they'll teach you a little bit about what's called tidal forces. This is the basis of something like that, where a change in the force of gravity across a body, across an object, means you have a different force down here than you do up there, and that's what gives it a center of gravity that's different from a center of mass. But that's all for the most part. 99-ish% of the time we're going to say, hey, center mass, center gravity, I'll use them interchangeably. Usually if we're balancing something, we're going to be more leaning towards a center of gravity type thing. If we're calculating a center mass, we're obviously going to be talking about a center mass of a type of thing. But just remember the difference there. It's probably not the biggest deal, but there may be some multiple choice questions that come up about it. And anyway, that's it. Keep going. Yay, physics, and bye, Rod.